you are responsible for knowing these 7 Maclaurin series. The one for 1 over 1 minus x shows up a lot on the AP exam, as does e to the x, sine of x, cosine of x. Less often, but still often enough that I want you to know them, is number 2 and 3 here, the natural log of the quantity 1 plus x, and the tan inverse of x. This shows up occasionally, again, enough that I would like for you to make sure that you have this in your notes. The first 6 are non-negotiable. You need to know those just immediately. Pay attention to the SIG and signs between each term. Some of these are alternating series. Some of them are positive series. What's listed out here beside each of these series on 1, 2, 3, and 7 are the values of x for which the power series acts exactly like the function. Remember, I've always said that on some interval very near the center point where the power series was built, that the function is going to be the exact sum of the polynomial or of the power series. Notice there isn't anything written beside those 3 functions. And the reason that there's no interval written there is because those series act like those functions for all real values of x. That makes them really powerful series. So they show up a lot. So these will need to be memorized for the AP exam. You will not be given enough time to generate them from scratch. I'm going to do one more example here to show you just how powerful knowing what these Maclaurin series expansions are, just how powerful that's going to be and how much of a time saver it's going to be. So pause the video now, make sure you make up flashcards or put these in your notes, and beyond today, you are responsible for knowing these. You will see these on quizzes, you will see these on exams, you will not be given enough time to generate them from scratch. Even though you could, you will not have the time to do it. So let's move forward and let's work this one final example. This says, let f be the function given by f of x equals e to the negative x squared. So f of x is e to the negative x squared. Part A says, write the first 4 non-zero terms and the general term of the Taylor series for f about x equals 0. And this is what an AP question would ask you to do. And what we would do is we would start with the known series expansion, and here it is right here. We would start with the known series expansion for e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. It says the first 4 non-zero terms, so that's all I should have to know. But it also says, and the general term. So the general term for e to the x is something I would automatically know as well. You're going to be expected to know the general term for e to the x as well. And just like we did on our substitution problem earlier in this lesson, we're going to take negative x squared and we're going to plug it in everywhere in the series expansion for e to the x that series has an x, even in the general term. That's how we're going to get the general term for e to the negative x squared. Look how much easier that is than generating the derivatives, evaluating the derivatives at 0, and so on. And so we could clean this up to be 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial. And frankly, that's the first 4 non-zero terms. And the general term would be negative x to the 2n over n factorial, and don't forget your plus dot 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 on the end. So that's what would be required to answer part A. All right, part B, use your answer in part A to evaluate this limit. All right, I'm going to try to get that where I can still see the limit there. I'm trying to get through this as quickly as I can because I really don't want a fifth video for this lesson. But I'm going to evaluate the limit as x approaches 0 of 1 minus x squared minus, and now I'm going to leave that blank, and this is all over x to the fourth. Well, notice that it said f of x is this function. And it says to use my answer, which is going to be this power series, to evaluate this limit. So I've got to put this power series in here. Over 2 factorial minus x to the 6th over 3 factorial, and so on. And we could put our general term in there as well. So that's how we're going to evaluate this limit. Well, we know how to evaluate limits. Let's see. That and that are going to cancel. That's 1 minus 1. Negative x squared plus x squared, that cancels. So this cleans up to the limit as x approaches 0 of, and all of this is going to be over x to the fourth, of x to the fourth over 2 factorial minus x to the 6th over 3 factorial. Put my general term in there because that is part of the result that I got from part B. And now I'm going to divide every term in the numerator. I'm just going to clean it up algebraically. Every term in the numerator by x to the fourth. So this limit cleans up to the limit as x approaches 0 of 1 over 2 factorial, x to the fourth divided by x to the fourth, minus x squared over 3 factorial plus dot 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 plus, and then I could just put, there's nothing wrong with me writing x to the fourth times n factorial. And now what I'm going to do is I'm going to evaluate the limit. Everywhere there's an x, I'm going to put a 0. And notice what happens for every term beyond the first one. So I can evaluate this limit. This limit is 1/2. All right, so not as difficult as it might first appear. All right, part C, write the first 4 non-zero terms of the Taylor series for the integral. And this is why I say we don't, like on that one example that we did, we don't get asked to integrate the general term very much in an AP question. Notice that now it doesn't say the general term, it just says write the first 4 non-zero terms. I want to leave part B up there so that I can use that series expansion. And now what I want to do is I want to integrate, because that's what it's asking me to do, the integral from 0 to x of e to the negative t squared dt is going to be the integral from 0 to x of this series expansion that we found when we were doing our work before. And now I'm going to drop that general term because part C doesn't ask me to include the general term. And so now what I would get is I would get t minus t cubed over 3 plus, this would be 1 over 2 factorial, 1/5 t to the 5th, and then plus 1 over 3 factorial, 1/7 t to the 7th, plus dot dot dot, and we're evaluating from 0 to x. So this would look like x minus x cubed over 3 plus x to the 5th over 10 plus, let's see, yeah, I did. Glad I caught that. That is a minus. So this is a minus. Minus x to the 7th over 7 times 6, which is 42, and then plus dot dot dot. So there's the answer to part C. Now let's see what part D asks us to do. It says explain why the estimate found in part C differs from the actual value of the integral by less than 1/200th. This is their way of getting you to recognize that you're dealing with an alternating series. Notice this is an alternating series. And we know alternating series error. The alternating series error has to be less than or equal to from the actual output of the function, which is that integral, from 0 to 1/2, from the actual output of the function, the actual sum minus any nth partial sum has to be less than the next term. Well, here's the term. Here's where we are on this integral, right? We're actually going to have to evaluate. I'll give myself some space here. So part D says we have from 0 to 1/2 e to the negative t squared dt. And so what we found here is we found the antiderivative for us was t minus t cubed over 3 plus t to the 5th over 10 minus t to the 7th over 42. And instead of evaluating it from 0 to x, we're evaluating it from 0 to 1/2. And so we want to know why that is different from the original by less than, I forget now what it said. Forgot my plus dot 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 there too. By less than 1/200th? Yes, by less than 1/200th. So we need the next term because that error is going to be different from 1/200th, or different from the actual output here by less than 1/200th. So we need the next term in the series. So what we're going to do is we're going to come back up here, and we're going to pick up the fact that the next term in the series, we could go all the way back up here. The next term here would be x to the 4th over 4 factorial. Let me get myself some space here. I wish these things would just go down just indefinitely, but they don't. All right, so I'm going to try to hurry. So we have x to the 4th over 4 factorial. We would have had to have plugged in that value. We would get negative x, well, we'd get positive x to the 8th over 4 factorial. And our error at x equal 1/2 would have to be less than our error bound would equal the absolute value of 1/2 to the 8th over 4 factorial, and we would have to prove that that was less than 1/200th. And that's usually how they ask you to answer these kinds of questions. So hopefully I don't get cut off, but this is 1 over 2 to the 8th times 24. That's 4 factorial, and we would just have to show that we recognize that's less than 1/200th. 2 to the 8th, 2 to the 8th. What is that? 2 cubed and 2 cubed and 2 squared. 8 times 8, 64 times 4. Wouldn't even begin to know how. You guys would be much better at that. That's 256. And that really probably would be all that we would have to show, is that at this point we would recognize 1 over 256 times 24 is definitely less than 1/200th. And that would be all that we would have to show to be successful on part D. So finally, there's the end of this lesson. Come to class next time. We'll work some homework problems.